So mathematical induction. So I say the first step is always to prove it true for the first case. And in the vast majority of cases, that'll simply be n equals 1. But just watch out because sometimes it's not. Sometimes they might say prove true for even numbers. So the first case would be n equals 2 and so on. Then we assume the result is true for just some random integer usually, but basically it has to match the condition of the question. So if the condition of the question was prove it true for even numbers, then I would assume k is an even number, and so on. And then I'll go and prove it for the next case. So I'm going to prove it's true for n equals k. I'll prove it true for the next case. Again, if I'm dealing with integers, the next case is going to be k plus 1. If it was even numbers, the next case would be k plus 2, and again, we just match what happens to be. And then, once we've done our proof, so we play around with the algebra, we go and prove it. It's really important we include something like this in our conclusion, because what we're saying is, okay, I've gone and proven this, but my proof is only as good as my assumption. So the way of writing that down is something like that is, well, I've proven it true for n equals k plus 1 if it's true for n equals k. Because if my assumption is not correct, then the whole thing's a piece of garbage, okay, basically. And then finally, we tie it all together and say, all right, well now I went and showed it was true for n equals 1, and then I can induce the rest. So the rest is true by induction. We can induce through all the possibilities. So as I said, we start with the series type, because not every series is arithmetic or geometric. So if I wanted to get a formula for this one, the squares of the odd numbers. And they're telling me the formula for this is a third n, 2n minus 1, 2n plus 1. And they want us to prove that this formula does indeed work for this number pattern. So the first thing I'm going to do, by the way, you don't have to write down step 1, step 2. I mean, this is just me sort of breaking it up. So we say, okay, these are the things we've got to do. Prove the result is true for n equals 1. You would write that down. Remember, it is a proof. You're explaining what you're doing. Okay. Prove the result, n equals 1. So on the left-hand side of this, well, the first term, when I sub 1 into the general term there, I get 1 squared is equal to 1. In the right-hand side, yes, the formula works. The sum to one term is in fact the same as the first term. So, yep, my left-hand side does equal my right-hand side. So, yes, hence, it works for n equals 1. So I'm going to assume it's true for n equals k. In this case, all k has to be is a positive integer. So k is some positive integer. I like to write down what it is I'm assuming so I can see it clearly. Basically, it's the question, but instead of using n, I'm using k. So that's what I'm proving to be true. Sorry, assuming to be true. I want to prove k plus 1. Again, I think it's key that you do write down what it is you're trying to prove, because if you don't write it down, how do you know when you're proving it? You need to know where you're heading. So now all it is, well, okay, I'm going to go up to the next term. So I'll replace n with k plus 1, and that becomes 2k plus 1 all squared for the last term. And on the right-hand side, replacing n with k plus 1, we'll get a third k plus 1, 2k plus 1, 2k plus 3. That's what we've got to go and prove. Now, with these series questions, remember, you're trying to get your assumption into your proof, because this plus dot, 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 I mean, who knows what's in the dot, dot, dots? We want to get rid of that and come up with something definite. And that's why I've broken it up. Remember, the first line there is the sum of k plus 1 terms. But I rewrite it to say, well, that's the same as saying the sum of the k terms, because that's my assumption, plus the k plus 1th term. So basically I'm saying I've got the sum to k terms, my assumption, plus the k plus 1th term. And I can substitute in my assumption, because remember, I'm assuming that that expression is true. We assumed the 1 squared plus 3 squared plus 5 squared up to 2k minus 1 squared was the third k, 2k minus 1, 2k plus 1. I've now got a piece of algebra I can play around with and hopefully get what they're looking for. Now, the temptation here is to expand the whole thing out and then try and factorise it. But don't do it. It's already partly factorised for you. Always look at the answer we're trying to get. What are the factors in the answer? And one of the factors in the answer you'll see straight away is 2k plus 1. We've already got a common factor in these two things as 2k plus 1. So why expand out only to refactorise? There actually is another factor there which you might not see. There's a factor in the answer that we have actually got there. And that factor is 1/3. You don't see it in the second one because it's got a coefficient of 1. But 1 is, of course, 1/3 times 3. So I can take that factor out as well. So if I pull out, well, actually, I didn't pull out my third. I'll probably do that in the next step. I pulled out my 2k plus 1. Yep, there we go. Then I pulled out my third. So I pulled out the two factors I know I've already got. That leaves me with k, 2k minus 1, and 3 outside of 2k plus 1. That's just going to be a quadratic. That's going to be a lot easier to play with and factorise. So let's tidy the inside up. We get 2k squared minus k plus 6k plus 3, which then becomes 5k in the middle. And yes, that does in fact factorise to be k plus 1, 2k plus 3, and that I think is what we were looking for. So hence, and this is what I'm saying here, concluded to say, great, I've proven it, but my proof is only good as my assumption. So hence, yes, I've proven the result to be true for n equals k plus 1, but it does rely on the fact that my assumption was correct. It relies on the fact that it's also true for n equals k. And so then the last thing then is to tie everything together. Oh, well, we go, okay, but hang on, I know it's true for n equals 1. Now, whilst we don't always write this down, you might see some conclusions that actually physically write this and say things like, well, because it's true for 1, well, now I know it must be true for 1 plus 1, so it's true for 2. Because I know it's true for 2, then I know it's true for 2 plus 1, 3, and so on and so on and so on for all positive integrals. Well, that's what induction is. So we don't need to write all that out. We can say, well, because I know it's true for 1, then it must be true for every positive integer value by induction. We can induce that solution through for every possible value. So that's the idea of induction. Let's have a look at another one. This one's in sum notation. Now, and trust me, no pun included here, but sometimes, okay, you might find it easier to actually write out the left-hand side so you get a feel for what the pattern actually is. And notice on the bottom of the fraction, I didn't actually work out the value of the number. I left it as 1 times 3, 3 times 4. And so okay, I see what this pattern is. They're talking about the denominator is 2 consecutive odd numbers multiplied together. I mean, that's just a personal thing. I like to write it out, and then I get a feel for the actual pattern itself. When it's in sum notation, all I can really see is the general term, and I'm not 100% sure, well, what does this look like? Up to you, of course, how you want to write that. Now, let's prove it for n equals 1 then. So left-hand side, the first term, that's the 1 on the 1 times 3, that's a third. Sub it in on the right-hand side, 1 on 2 plus 1, yep, that's also a third. So good, it works for n equals 1. So I'm going to assume it's true for n equals k. So basically, same statement there. I'm just replacing the n's with a k. Now I'm going to prove it true for k plus 1. So again, I'll just add in the last term. And then on the right-hand side, I'm replacing the n's with a k plus 1. So that's what we're going to try and prove. All right. Again, it is a series type, so I'm going to rewrite it as the sum of k terms plus the k plus 1 term, because that now allows me to substitute in my assumption. And we assumed that was all equal to k on 2k plus 1. We want to end up with k plus 1, 2k plus 3. Well, the final answer is a single fraction. And we've got the sum of two fractions. So I guess the logical thing to do is treat it like an algebraic fraction question. Let's add these together. So the common denominator will be 2k plus 1, 2k plus 3. And on the top, I'll have k outside of 2k plus 3 plus 1. All right, expand the top out. 2k squared plus 3k plus 1. Now, this is where a little bit of, no, fudging is not the right word. It's not cheating, really. But I know what that's got to factorise to be. I don't really have to think about it too much. Because I know it's got to cancel to give k plus 1, 2k plus 3. Therefore, logically, this must factorise to be 2k plus 1, k plus 1.
Cheater.
Well, it's not really cheating. I mean, it's true. But what I'm getting at is, rather than struggling to think about how does this factorise, use a bit of logic. And I'm not saying just leave it like that. Check, make sure that there's not something silly there, and go, oh yes, that does expand out to give the right thing. Right? That sometimes is going to be quicker than trying to factorise the quadratic. Okay? And what do you know? 2k plus 1 cancels. Oh, that was lucky. And so we get k plus 1 on 2k plus 3, and that is what we're looking for. You say, yep, it is true for k plus 1 if it's also true for k. And so then we just finish off our solution by tying everything together. Yep, well, back in step 1, we proved it was true for n equals 1. So then via our proof that we just did, we now know it's true for all of those values by induction. All right, now, 6n is just on induction. I've broken induction up, I guess, into 3 different types of questions. So we are going to spend the next, well, we've got 4 periods tomorrow, so the next few days just looking at induction. We'll see how it goes.